This is the video solution to one of the Bernoulli equation example problems. The pipe in the figure to the right is transporting oil with a density of 800 kilograms per meter cubed. The velocity at point 1 is 5 meters per second, but at point 2 it's 10 meters per second. Calculate the difference in height in the two open thin tubes. So I'm going to call the lower tube height h. I'm going to call that my starting point is h equal to 0. And here's my strategy. I'm going to use rho gh as the gauge pressure, where h is the height difference between the two vertical pipes' fluids. So that's kind of different. That's why I wanted to make h equal to 0 at the lower height of the two tubes. The gauge pressure is P1 minus P2, where P1 is the pressure below the vertical tube and P2 is the pressure below the other vertical tube at point 2. So it's not the pressure in the tubes, it's the pressure below, right below those tubes. The pressure P is pushing the fluid up the vertical tubes, and that's the P at those locations 1 and 2. P1 minus P2 can be found by rearranging Bernoulli's equation as well as using the hydrostatic pressure equation, or the pressure at depth equation as we've called it on occasion. It can then be set equal, that is, the gauge pressure can be set equal to the rho gh to solve for the height difference in the two vertical pipes. So what I'm going to do is use Bernoulli's equation and the hydrostatic pressure equation. I'm find both for P1 minus P2 and basically set the two equations equal to each other and find h. And notice that I changed h a little bit to call it delta h for this expression. So if I look at this in terms of the givens, I know that the velocity at 1 is 5 meters per second. The height, don't know. It's one of the parts I'm going to look for. The density of the oil, the velocity at underneath point 2 is 10 meters per second. And I'm going to call that height above number 2 equal to 0. Alright, so I'm going to erase that so I have some room. If I look at the hydrostatic pressure, that's going to be P1 equals P2 plus rho gh. That's what we sometimes call the pressure at depth. And then the gauge pressure is just P1 minus P2. So when I rearrange the equation, I get that just to be rho gh, or rho g delta h actually. And the h is the height in the two tubes. Now let's switch gears and look for gauge pressure with Bernoulli's equation. So Bernoulli's equation is the pressure is equal to 1/2 rho v squared plus rho gh, this at location 1. At pipe number 2, it's the pressure at pipe number 2 plus 1/2 rho, the velocity underneath pipe number 2, plus rho g and the height in pipe number 2. Now when I'm looking at this, points 1 and 2 are the same height, so the heights are going to go away. And that's going to make my life a little bit easier, so my equation gets a little bit smaller. Now I need to rearrange this for P1 and P2. So what I'm going to do is I'm going to move P2 over, and then I'm going to take my other expression and move it to the opposite side for 1/2 rho v1 squared. Move that over, so now I've isolated the gauge pressure all by itself. Great. So P1 is equal to 1/2 rho quantity v2 squared minus v1 squared. So I use the distributive property to pull out the 1/2 rho, just to make the math a little bit easier. Alright, now P1 minus P2 from Bernoulli's equation equals P1 minus P2 from the hydrostatic depth equation. So that what that means is in red, you can see it's rho gh, that's a hydrostatic pressure equation, equals from what I got the expression from Bernoulli, 1/2 rho quantity v2 squared minus v1 squared. So if I solve this for h, I can take it 1/2 rho times that quantity divided by rho g. The rho's divide out, leaving me with 1/2 v2 squared minus v1 squared divided by g. Put in my numbers, and I get the height difference between the two tubes to be 0.261 meters. It's about 26 centimeters, or a little bit less than a foot.